To introduce Denis Bonheure from University Libre de Brussels, and let me just give some short introduction. So he did his baccalaureate at the University of Brussels. Then his master thesis he did in University Catholic de Louvain. Also here he did his PhD. Let me mention that I look on his CV and I think that you really like to travel a lot, and it's very interesting. And you visit many places when you were invited in Italy, France, Spain, Finland. Also, you have been in Prague, Germany, Argentina, Brazil, and so on, and of course United States. And let me also mention that you got several awards. So the recent one is from 2019. It is award of Adolf Vetrams. I don't know if I'm pronounced well. Also, you got twice this award of Socrates, and also you got this award of Jacques Derrida in the period of 2008-2012, and also another prize of Académie Royale de Belgique in 2005. So it means that you are really working very, very well. And today you will speak about the article common with Giovanni Paolo Galdi and Filippo Gazzola about equilibrium configuration of a rectangular obstacle immersed in a channel flow. So please.
Thank you. Thanks a lot for the introduction, and thanks a lot for the invitation. It's a great pleasure and an honor to be a speaker in this Necas seminar. Well, when I was a student, Necas was a very strong names in the things I learned. So it's really a pleasure. You see that I put a picture of Prague. Prague is a very nice city, and you will see why I love Prague so much. You see all these bridges, and you will directly see that one of my motivation in my research, my current research, is oscillations in bridges. You probably know those two bridges. If you look here, those are the Tacoma Narrows Bridge. On the left, you have the new one. On the right, you have the old one, which collapsed and was rebuilt. And so I'm not going to discuss this story of the Tacoma Narrow Bridge. I believe all of you know quite well the story. So let me just show you a picture of a bridge. So in fact, a bridge is really a complicated structure because you have to take into account the towers here, and then you have, of course, the cables, and you have the anchors. Okay, and then of course you cannot study the movement of the main span in the same way I have the small span, the side span, because from obvious reasons. Now, it's true that Prague's bridges are not suspended bridge, so what I'm going to discuss doesn't really count for those bridges. But this picture shows you that the structure is complicated, so I should beware everybody that I do not, I'm not saying that I will give any hints on bridge, but I will study plates. So I will totally simplify the model, and my discussion is now about plates. And the plates is, let's say, I'm discussing the main deck, okay? And I totally forgot the main cables, and I totally forget the anchors. So really, what I will discuss is you have a plate which is fixed on the small edges here and free on the large edges. Okay. Now, this is a CFD picture where you see that you have a flow coming from the left, and encountering an obstacle, and you see that there are two things, at least, many more things, but at least two things count. The ratio, you see that the flow patterns here is quite different. If you have a long obstacle, then you have the vortices close before the end of the obstacle. So you have quite different patterns. So the ratio is important, and you also see that the shape is important. If you have this here, this shape here is more like a realistic bridge. Of course, these are cross section of bridges. If you see that you have wind guard here, this creates huge vortices here. So this is not good for cars. But if you have smaller obstacle on the bridge, I mean, on the plate or on the cross section, you create different flow patterns. So it's quite a difficult thing to study. So I will totally simplify things, and my cross section will always be a rectangle. So I'm not saying that I'm close to reality. I'm simplifying in order to be able to say something and to study something from the mathematical point of view. Of course, engineers, they can do much more, but my point of view is mathematical. So this is an experiment in wind tunnel. You see that this is my simplified, this is my simplified structure here. So it's really a plate which is fixed on the two sides, right? And you have a flow coming from the left, a wind generated by the wind tunnel. And you see that you have many vortices created after the bridge, after the plate. So the obstacle, when the flow hits the obstacle, it generates a lot of vortices. So this is what is called vortex shedding, and I illustrated like this. So in fact, when you have, this is a cylinder which can move only up and down, you have a wind coming from the right, and you see that this wind creates vortices, let's say, in a periodic way, and you see that it starts oscillation of the cylinder up and down. So that's if I come back to this Tacoma bridge, remember that when the bridge collapsed, you had a strong up and down movement, and after some moment, the deck started to have torsion, and the torsion was a disaster that created the collapse. Now, what we suspect, and what is, I think, a good explanation of what happened, is that when you have a wind coming here, it will create up and down oscillation. So this is an excitation of the bridge by the wind. And once you have energy entering the system, then you have several modes in the structure that can capture energy from up and down movement to torsional movement. And this torsion will be the devil, let's say, for the bridge. Okay. So let me comment a little bit more on what is the mechanism that creates this up and down movement of the body in the vortex shedding phenomenon. This again CFD, and you see that you have two shapes, and these shapes are symmetric. And in fact, let me just indicate that this is a picture with small Reynolds number. And you see that the pattern is totally symmetric. So for the moment, forget about inflow, outflow. Of course, maybe it's not very physical. Maybe I have to go to an infinite cylinder and so on. But just assume that, okay, look at the symmetric. Okay. Of course, if the solution is totally symmetric and there is no lift. So lift is the force that the fluid would create to go like this, and there is no lift. Of course, there is drag. drag is in this direction, but there is no lift. Okay. Now, if you increase the Reynolds number, you see that you have a non-zero, you have non-symmetric pattern. And assume again that I'm not discussing anything about the boundary condition and etc. So just do the reflection here and like this. If you have good condition, no sleep and good inflow outflow, let's say, you can flip the solution, okay, and you will have another solution of your Navier-Stokes equation. Okay, so if there is non-symmetry, there is non-uniqueness. So what does it mean? It means that the fact that there is lift created by the flow is a quite difficult phenomena to capture from mathematical point of view, because it means you are in a regime where Navier-Stokes does not have uniqueness. Okay, so that's quite an explanation of why this is a difficult problem. Now, you can imagine that going from this small Reynolds number to this bigger Reynolds number, you would see bifurcation phenomena. These are stationary solutions. So you can, let's say, from a mathematical point of view, analytical point of view, when you lose uniqueness, you always think about, okay, probably there is a bifurcation somewhere. And you have to be careful here, because bifurcation, well, it's not, numerically you can observe bifurcation, but what is interesting here is that there is a bifurcation which appear before the bifurcation of steady state to steady state, from symmetric state to non-symmetric state. And this is now a time-depending solution. And in fact, when you see this time-depending solution, you have the feeling that this solution is going to converge to a steady state. It seems like that. And then you will see that at some moment, the solution will start to be non-symmetric. And maybe you have seen this kind of video before. So you see that the solution is not symmetric here. It becomes to be non-symmetric, and then it starts. And then you see that what is called a Karman vortex street is created. And in fact, this is what is called a Hopf bifurcation, because you bifurcate from a steady state to a periodic state. And it's interesting that in 2D, when you look at a flow past a cylinder, the Hopf bifurcation appear before the bifurcation of steady states. And by the way, there is a marvelous paper by Paolo Galdi about the functional setting of this bifurcation, this Hopf bifurcation. Okay, so what would be a dream? A dream would be that we can show, or I would dream, excited by a wind, it starts to oscillate up and down, and periodic movement, maybe twist movement of the bridge, of the plate. Okay, so let me discuss about modeling.
Yeah. So in your previous graph, I always thinking about steady state, and you increase the Reynolds number.
Yeah.
Okay, and like when Reynolds number is small, you have symmetric solution. When the shape is symmetric, and when you increase the Reynolds number, then somehow it becomes non-symmetric.
Yeah.
Right? Okay. Yeah. Thank you.
Yeah, that's it. Okay, so let me discuss the modeling. So there are at least 3 levels of modeling. One is to study the structure. And when you want to study the structure, somehow you assume how the aerodynamic forces act on the plate. So, for instance, I will show you two ways to introduce aerodynamic forces on a plate equation, but somehow there is a limitation of this model because the way you assume the wind is acting on the plate is empirical. There is no really, it comes from a theory. It's not really totally physical. Now, there is another level of modeling where you can study how the fluid reacts to a movement of the plate. So in this case, you assume that the structure is either fixed, and then you look at the different pattern, the different solution you can have around this obstacle. This is the fixed obstacle problem, let's say. Or you can prescribe a motion of the plate, and then you see how the fluid reacts. Again, there is a limitation of this level of modeling because you prescribe either that the structure is fixed or that it has a given motion. And then there is the much more realistic level of modeling, which is the so-called fluid structure model. And in this case, you couple the fluid to the structure. So you take into account that your plate is going to move because of the presence of the fluid. And when the plate starts to move, of course, the fluid reacts. And also, let's say the solution of the Navier-Stokes governing equation is going to change, okay? So it means that you have to take into account the forces that appear on the interface where the fluid meets the structure, okay? Now, let me give you, let me do a little bit of advertisement. I don't know if you are able to recognize this man. It's a true picture. It's a picture from a book written for children. I don't know if someone knows who it is. No answer. Okay, it's Vladimir Mazia. In fact, Vladimir Mazia likes to write a book for children, so he's also a writer. So in this paper I wrote, it's a survey paper I wrote dedicated to Mazia. We discuss some questions about this different way of modeling, different level of modeling. Now, I realized that maybe it was better to give a talk which is not so much technical and maybe based more on the results. So I will discuss the modeling of the structure I did in two different papers. One with Dos Santos from Brazil and Gazzola from Milano. And another one again with Gazzola and Lasieca and Webster from United States. So in the first one, we somehow study the structure. I will show you the equation. And we assume that the vortex shedding is modeled through the presence of a periodic forcing acting on the plate. And in the second paper, we take into account a non-conservative effect acting on the plate, and in fact, this is coming from piston theory. So let me show you that. So this is the model. I'm not going to discuss everything because there is too much detail, but important thing is that you have the wind coming from one side, and then you have your plate. This is fixed on the small edges, okay? And this is free to move on the large edges, okay? Of course, you can have more difficult, more realistic shape, but I'm not going to discuss this. I'm just supposing that I have a true plate. Now, this is the equation we studied, and you see that there are different features to take into account. So this, of course, biharmonic operator is coming from the bending energy of the plates. You have a damping. You see that the nature of the equation is more or less hyperbolic, even though it's degenerately hyperbolic because you have first order and not second order. And then you see that you have this non-local term. If you want, you can read all the physical constants that appear in the model. Okay, so the way we handle the aerodynamic forces, in the first paper we used a periodic forcing term which was proposed by some engineers. And the thing okay, when you say you have something periodic, first thing to write down is, let's say, a sine or a cosine. So this is not really important. The important thing is that the frequency is governed by a law which is linear in the wind velocity, while the intensity is quadratic with respect to the wind velocity. And this is again empirical. There is no real physical explanation of this. Okay, so that's a way you can model the vortex shedding, but okay, it has a limitation because you see that this force is totally given and depends only on the wind. It does not depend on the way the bridge moves, on the way the plate moves. Okay. Now another tentative that we did is with this kind of non-conservative term, and you see that again this W is the speed of the wind, but you have now this uy, sorry, derivative of u with respect to y. So somehow you see that the way the bridge or the plate is forced depend on the movement of the plate, on the deflection itself, versal direction. So remember that the y is this direction here, right? Let me show you, well, this is again the model, just to emphasize that you have this non-local term here that multiply this uxx, and this non-local term is in fact, I think I have a picture, yeah. This non-local term, there is what is called the nonlinear stretching here and the pre-stressing here. Now the pre-stressing, it means that you can have a totally flat bridge, or you can have a bridge which, so totally flat is like this. Oh, sorry, it's not very well. Like this, and pre-stress would be like this, okay? And you see that this one is a little bit more pre-stressed. You cannot pre-stress too much a bridge because you can imagine that if you put too much energy, then your bridge, your plate is not going to react in a good way. So this is, let's say, equilibrium 0, and this is a shape which is like the first eigenfunction of the problem. So it's very close to a sine, and it is a sine, in fact. Okay, if you put too much energy when you pre-stress the plate, then your plate is going to look like that, and that's not what you want. Okay. Okay, so these models are these non-local models. I mean, we took some ideas from Bergreen and Berger. Okay, so this is in dimensionless form. Here the equation. So you have a damping, you have the pre-stressing, the nonlinear stretching, and then you have an external force. And what we want to analyze is, I will discuss this boundary condition here. What we want to analyze is when you have an external force acting on the plate. Imagine that you know that you want your plate to resist to an external force which has a prescribed bound for its intensity. You want to know, how much you have to damp your structure to resist to this external force. Okay, so now let me just discuss the boundary condition. So as I said, on the small edges, U and UXX, in fact, this is a natural boundary condition. U and UXX are 0. And then on the large edges, you have a quite strange boundary condition. So you have this boundary condition which involve UYY, UXX, but also UYYY and UXXY. Okay, this sigma I will not discuss. It's a Poisson ratio of the plate. So it's something related to the fact that either the material is stretching or enlarging when you compress or when you stretch it. Okay, it's a positive constant. Well, it could be negative in some case. There are some foams who have negative Poisson ratio. Okay, now let me discuss this. How when you look at the plate, a very simplified model of that, the energy of the plate, depending on the deflection, is quadratic with respect to the principal curvature of the plate. And you have here a term which is sigma K1, K2, so the product of the principal curvature. Now, if you have small deformation, this sum of square here can be approximated by the Laplace of u to the square, and the product of the curvature is the determinant, is approximately the determinant of the Hessian. Okay, and so this is what people call Kirchhoff law theory, and so you have this energy, which is a nice approximation of the bending energy of a plate. Okay, and now you see why my boundary conditions are what they are. It is because I'm taking the Sobolev space of functions which are 0 on the small edge, and that's it, only that. And then I take my inner product to be dictated by the form of the bending energy. So I put indeed sigma minus 1 times the bilinear form, which gives the determinant of the Hessian when you take u scalar u dot u. Okay. And so this boundary condition, that's how the boundary condition. Oh, sorry. I should this. This boundary condition. These are the boundary condition that appears when you go from weak formulation to strong formulation. Okay. Of your solution. Okay. So and again, as usual, weak solution is stood in the classical. I mean, this is a classical definition of solution. So, for instance, we ask that U is continuous in my space H2 star, C1 in L2, and C2 in the dual space of H2 star. And this is because you want this to be defined, you want this to be defined, and you want this to be defined. Okay, and that's it. Okay, so we can prove well-posedness and in fact also the existence of strong solution if you assume a little bit more on the initial condition. And this is, I mean, it's not what you need, but that's what you can prove. There seems to have a gap. You have to assume G to be C1 in order to I mean, with classical tools, and we were looking in the literature, but it seems that there are no results if you don't have this assumption. Okay, so with respect to this inner product and this space, a nice thing you can do is that you can separate your space in a subset of even function with respect to y and odd function with respect to y. Okay, and those functions are orthogonal, and you have a direct sum, which give you your solution, your full space. Sorry. And so any function, any solution can be decomposed in a longitudinal part and a torsional part. And remember that I told you in the beginning that what is bad for a plate, it's when there is a folding, when there is torsion. When there is a longitudinal or displacement, it's not too bad for the plate. Okay, so these are the spectral decomposition of these two spaces. This is in fact what I was saying, like it's a phi1. It's a eigenfunction of an associated buckling problem, which depends only on x. This is a torsional eigenfunction, so let me call it like phi1 torsional. This is phi1 longitudinal. This is phi2 longitudinal, just to show you an idea of what these functions look like. And this is a phi2 torsional. And you see that this one is bad because this creates cracks on the structure. Okay. What can we say about this? That was the question I told you about. Assume that your external force is bounding, so you have you know explicitly a bound on this external force. So in application, it could be you know that you are in a region where the velocity of the wind is never above a certain threshold. And then you can prove that there exists a damping delta zero, which is enough. If you damp your structure more than with a delta more than delta zero, and engineers know perfectly well how to damp structures, then in fact your plate will be what we call torsionally stable. So what do we mean by that? We mean that the torsion zero exponentially fast at infinity. Okay, we are existence of periodic motion and stuff like that, but I'm not going to discuss here these things. Okay, this is the second contribution we had. We added a term which is non-conservative, and that comes from piston theory. And if you add this term, you cannot. I mean, you can decompose your space in longitudinal and torsional movement, but of course, this this one is this one creates if you because of this new term, if you start with a initial condition which has no torsion, it doesn't mean that you will never have torsion. Okay. Okay, so things are a little bit more complicated here. So what do we get as result in this case? So we have a theoretical result about existence of attractor. We have a stability result. So if we assume that this G is 0 and we only take this aerodynamic piston type forcing term, then we can prove that if alpha is small enough, indeed all the solution converge exponentially fast to 0. And we have something much more interesting, I think. We were able to show that if alpha is big, and in fact, we can prove existence of stationary solutions which are not the equilibrium solution. So somehow it means that if alpha is big, and this alpha is a aerodynamic coefficient. It depends on some physical, physical engineering way of putting of taking into account the non-conservative force. If this alpha is too big, in fact, the model has more than 0 as steady solution. So, and we have many steady solutions. And this means that somehow the plates can be in equilibrium in a different position than the 0 position. Okay. Okay, and now I discuss more in details about the title of my talk. So the angular body in an infinite channel. So this is again related to what I want to understand, the movement of plates or bridges. And here we assume only that we look at the cross section of the body. So we look only at the cross section of the plates, and we have a wind or a flow coming from the left. And we want to understand if this flow creates like movement up and down, but also we want to understand if this starts torsional movement. Okay, so that's what I show here. This is the up and down. And this is rotation of the plate. Okay, here I put the cables just to illustrate things, but I'm not taking cables into account. Okay, so what we wanted to start to study is this obstacle in a channel flow. And we wanted to understand now the level of modeling of a fluid structure interaction between the flow and the structure. Okay, so the idea is the following: you have a flow coming from the left, and in fact this will be a quasi flow at infinity. And this flow is acting on the body, and you want to understand which stationary solution can be an equilibrium solution. This is the first thing to understand. Of course, you can try to understand the dynamics, that's something else, and you can try to understand bifurcation from an equilibrium, that's also something else. So first things to do is to understand if there are only one or several equilibrium positions. We had to treat separately the up and down movement and the rotation. So up to now, we don't allow 2 degrees of freedom at the same time. We either allow that the obstacle moves up and down the channel, or we allow to rotate around a fixed pin. Okay. Now this is the equation, and you see that fluid. Okay. The fluid domain, of course, it's the channel, it's the body. The position of the body is depends on the position of the barycenter of the body. Okay. Now we assume that the fluid is governed by the incompressible Navier-Stokes equation. So of course we have this divergence-free condition. This is T is the Cauchy stress tensor that I recall here. For those who are not familiar with this, of course, this term here is a gradient of pressure minus Laplace. Okay. This is what I said before. I'm assuming that my flow is Poiseuille at infinity in minus x1 and x1. Okay. And it's a parabolic Poiseuille. Okay. Now I put non-slip boundary condition on the channel, and this here, this is the dynamical fluid structure condition. Okay, it means that at the interface of the body with the fluid, the velocity of the body and the velocity of the fluid coincide. Okay, and now that's another fluid structure interaction condition here that we assume. We assume that the body is moving because of the lift force that the fluid creates on the body, but also because of a nonlinear restoring force. And why we do that? Because if we think about the fact that this is a cross section, okay? So if this is a cross section, my full plate is like that, and somehow a cross section cannot have wild oscillation. It's not totally free to move because of the plate, which is fixed here. Okay, so there is kind of a restoring force, okay, that we assume to be a nonlinear restoring force. Okay, so that's again the problem. And oh yeah, what do we assume moreover on the restoring force? We assume a strong force condition. So of course we assume that the force is acting when the cross section is above the zero position. The restoring force is recalling it to the origin, and the same when it's below. And we put an extra assumption. We assume that the force satisfies a strong force condition when the cross section is too close from the wall of the channel. Okay. In fact, this strong force is there to prevent collision. So that's what we want to study. We want to study equilibrium position. So you will not depend on T. H dot is going to be 0, and H dot dot is going to be 0. So if we want to study steady solution, steady fluid structure solution, what we have is Navier-Stokes equation, Poiseuille at -infinity and +infinity in the x1 direction, and non-slip condition on the obstacle and on the wall of the channel. And of course, we can solve this. This stationary problem is solvable whatever omega h. So omega h, remember, that is the fluid domain, and the fluid domain is the channel minus this obstacle here. So whatever the position of this obstacle, this is solvable, and there is a solution. And if lambda is small, it's even unique. But we don't want this. We want a solution which satisfies the fluid structure interaction condition. So this was the condition here, this condition that appear here on the third line. So it's exactly asking that the restoring force match with the force coming from the fluid to the body. Okay. Okay. I think I still have a few minutes.
Yes, I think you have, yeah.
Yeah, okay. So let me discuss the second problem where when the body is rotating into the channel. Of course, now the fluid domain is a little bit different. Is the channel still minus the body, but now this body is rotating around a fixed pin. Okay, so it's rotating around the center of mass, and you have a very similar problem still with the Poiseuille flow. Again, the Navier-Stokes equation, but a change on the dynamic condition at the interface. And of course, now what you have in the third equation, it's a kind of pendulum equation with a non-linear restoring force. And this is what is called a torque. This one is a torque. So just telling you that the body prefers to be horizontal, and when it's rotating, then there is a restoring force. Okay, so what do we assume? We assume that this restoring force is odd, derivative is positive, and we don't have to assume any strong force. It's a weak force condition. So just that when the obstacle is not horizontal but vertical, the recalling force is infinite. Okay, and so the problem to study is again equilibrium position of the body in the channel. And so what you see is that you have this Navier-Stokes condition and no slip boundary condition. Okay. Okay, so what is the result? In both cases, what we were able to show is that when the Reynolds number is small and when the intensity of the Poiseuille flow is small, then there is uniqueness of the equilibrium position, which is obvious, let's say, from the physical point of view. And if physics or some engineers, he will start to laugh because, yeah, of course, this is true, but prove it with mathematical rigor. That's a different story. Okay, so there is a R0 and a lambda 0 such that if the Reynolds is small enough, if the intensity of the Poiseuille is small enough, then there is a unique stationary solution which satisfies the fluid structure interaction condition. So there is a unique equilibrium solution in the case of the movement up and down, or in the case of the rotation, in both cases. Now, you have seen that in orange, I discussed the up and down motion, in green, the rotation, and in blue, it's something which is true for both. In fact, I will have to discuss differently the up and down movement and the rotation, but some stuff can be done in a unified way. For instance, existence of the stationary solution. Each time you prescribe a position of your body, you can prove that if the Reynolds and the intensity, so the product of the Reynolds and the intensity is small enough, then in fact, the stationary problem has a unique solution. So it's weak, and it's in fact it's unique in the class of weak solution. Okay. And moreover, what you have is that you have universal bounds. Okay. So the gradient of U in the fluid domain will be bounded in a good topology. Of course, this depends on the position up and down, and this depends on the position, angular position. Okay. Now I have to discuss differently the case where the plate the obstacle is going up and down, and this is because in this case there is an additional difficulty, and let me explain this. So in fact, to identify this lift, this is the lift in fact. So to identify the lift acting on the obstacle, the trick is this is not new, this is known for many years, is to introduce some auxiliary fields. Okay, and take the condition on the boundary of the obstacle. So we introduce this auxiliary field flow, and this creeping flow is not so good. Why? Because you see that it's zero on the boundary of the channel, but it's equal to E2 on the obstacle. So when the obstacle is close to the channel, to the boundary of the channel, of course there is a boundary layer. You cannot expect the solution to be regular. There is a boundary layer, and we were able to quantify this boundary layer, and we have a bound which is the following: the gradient of this W in H2 is bounded by a constant which depends on nothing, times the distance to the boundary to the power minus 3/2. Yeah. Okay, and that's the reason of the strong force condition. Remember that I had put a strong force condition on the restoring force. That's because we lose control of how the lift is close to the boundary. Okay, and we have to quantify this. Now, when you have introduced this auxiliary flow, what you can show, and this is just you multiply the Stokes equation by the solution of Navier-Stokes. Sorry?
Like, what is epsilon here? Like
what is epsilon?
Yeah.
This epsilon,
sorry.
It's the distance from the wall.
Okay. Thank you.
Okay. So when the solution is when the obstacle is too close to the wall, there is a boundary layer. Because your derivative jumps from E2 to 0 on the wall. Okay. And that's the quantification of this boundary layer. Okay. Now, if you multiply the Stokes equation by the solution of Navier-Stokes, and on the other way around, the equation of Navier-Stokes by the creeping flow, the auxiliary flow I introduced, you end up with this. Is that integral, and that's important that it's a solid integral, where you see that the Reynolds number appear. You have the solution of Navier-Stokes and the auxiliary flow, W. Okay, and this is a very good information because, for instance, it shows you that Stokes tells you that there is no lift. Okay, if you have a Stokes flow does not produce any force on the obstacle. Okay, I mean, you know that there is this D'Alembert paradox for Euler flow. So for a Euler flow, there is no lift. And this is again true for Stokes. There is no lift for Stokes. And in fact, Navier-Stokes, as long as you have uniqueness of the solution of Navier-Stokes, there is no lift. If you are in a symmetric situation, you need to have symmetric situation. Okay. Okay, so let me skip this proof. This is just integration by part. Okay. Now, how to show that you have uniqueness of the position of the equilibrium position is the following way. You replace, well, you define the function psi with the restoring force plus the lift. And you know that your solution is a solution if and only if this function is 0. Okay, and so what we want to do, we want to show that if Reynolds is small enough, then there is only one solution to 1,0 of psi, and this is h equals 0. Now there is a big stuff here. You have to prove, well, since we are going to argue with implicit function theorem, you have to prove that this function psi is C1, depending on the position of the obstacle. And this is a shape derivative. And this goes back to Murat and Simon. Okay, I don't show any details because it's quite heavy. And then what you can show that due to the symmetry of the problem, when the obstacle is at 0 position in the channel, this function is 0. Okay, and so now you use the lemma to replace the lift by this solid integral here, and so now you are led to study the 0 of this f of h minus this integral. Okay, and by the way, you need to prove that it's C1, so that's why you need a shape derivative in this, because your integral depends on the fluid domain. Okay, and it has only 1 0. You are in 3 steps. First step is when h is small. The fact that you have a unique solution will come from the implicit function theorem, because you prove that the dh of psi at 0 0, this is f prime of 0, and by assumption it's positive. Okay, so it means that for small Reynolds and small gamma, the 0 is the only solution of the only 0 of psi. And then you have 2 other configurations to study. The one where when you are close to the wall, when you are close to the wall, you have this estimate here. And that's where you use the strong force assumption, okay, to deal with that situation. And then the intermediate region is just by a compactness argument. Okay, so let me just show you my last slide, just telling you that same thing can be done for the rotation. And I'm sorry I was a little bit long, but I thank you very much.
Thank you very much for your very interesting, very nice talk. So